Hi, I'm Jacob. In the next 5 minutes, I'm gonna talk to you about causality, specifically partial identification, which is my research, and then add some applications in the real world of partial identification. Let's go. All right, let's take a look at a graph together. Here we have chocolate consumption and number of normal laureates in the country. And we see that Switzerland is doing pretty well, while other countries are still trying to catch up. Now, does it mean that they should start to eat more chocolate? Obviously not, because correlation does not imply causation. Now, what does imply causation though? That's the question we try to answer in causal inference. So let's take a look at that. So, what's the key question in causal inference? It is all revolving around something called identifiability. And identifiability means that we can calculate the effect of interest from the data available. Now, either your effect of interest is identifiable, so yes, we can calculate it with the data and the maths, or it is not identifiable, so no, we cannot identify it. Now, with partial identification, we're trying to go the middle road here, in that even when you can't fully identify the causal effect, you still get bounds on the true effect of interest. So let's take a look at that together, how that looks like. Let's take a look at aspirin. It's a very popular drug to treat headaches. When you go to the doctor will give you a prescription, Z here. And that, again, will lead to you actually taking aspirin or not. That's your decision X. And finally, you taking aspirin will have an impact on your headache. Why? When you want to answer the question of what's the causal effect of aspirin on your headaches, we're interested in this relationship here. Now, this relationship we can easily quantify mathematically, as long as there are no unmeasured confounders. If there is an unmeasured confounder, for example age, then this will bias your effect estimation. We see that here that age can both impact the way you take aspirin and also the way you perceive headaches. Now, in partial identification, we take a next step and we evaluate the whole causal system by looking at all possible ways you can react to your treatment. So we're looking specifically at this relationship between, for example, your prescription and actually taking aspirin. And in a binary setting, so let's say X is only ever 0 or 1, where 0 means you don't take aspirin and 1 means you do take aspirin, we have only 4 absolute possible ways for you to react to the prescription. First, we have compliers, patients that comply with what the doctor says. Prescribe aspirin means taking aspirin, and no aspirin prescription means not taking aspirin. Contrary to that, defiers will always do the opposite of the prescription, defying the doctor's recommendation. Finally, to complete the set of all possible responses, we have always takers who will always take aspirin, and never takers who never take aspirin, regardless of prescription status. With all these responses specified, we can now construct a linear program where the maximum is the upper bound and the minimum the lower bound of the causal effect of aspirin on headaches. And now that I've explained partial identification, let's take a look at some real-world application. Here, on this example, we have Joe, who recently applied to a mortgage application, but he got rejected because he didn't make it across that orange threshold. So now Joe's asking, how can I make changes to my life to be accepted next time I apply for the mortgage? He has a salary and he has savings. So what changes or what interventions can create causal effects such that he will be able to cross this threshold? First, we describe Joe's situation with a causal graph. Salary influences savings as people change their savings habits with increasing income. Both salary and savings are commonly used to assess mortgage applications. Realistically, all of these variables are confounded, which would bias a point identification. But with partial identification, we can identify possible interventions that can reliably lift Joe above the acceptance threshold. Generalizing and scaling partial identification towards more complicated scenarios brings challenges, and in my research, I developed solutions to overcome them. So this is how Joe can make a calculation how to get his mortgage loan approved next time. So let's sum it up a little bit here. Causality is really important because correlation does not imply causation, but identification isn't always possible. So partial identification, which is my research, looks at how we can still make informative decisions, even when there is no full identification. And now with these applications with Joe, we can actually get better recommendations and decision making in finance and in algorithmic fairness. Thanks for listening to my video, and let me know if you have any questions. Just feel free to reach out.